So now that we understand exponential functions, let's talk about a specific exponential function. And this would be a compound interest exponential function. And in this situation, it is interest compounded nthly. Nthly. All right, so we have a of t. A of t is the end amount at time t. P is my principal or my initial amount. So it's what we start with. R is my rate. So we've got R here. R is my rate. And whatever we use for our rate, we need to take that percentage and make sure it's turned into a decimal. Okay, so 5.2% would be 0.052. You need to divide by 100% and move the decimal 2 places to the left. T represents our time, and then we have this other value here, N. Okay, so nthly. N is the number of times compounded. So if you read a problem and you read quarterly, that might mean N equals 4. Or monthly would mean N equals 12 because there are 12 months in a year. There are two that I think get confused, so I'm going to squeeze those in here. Biannually and semi-annually. Biannually is every other year. So in that situation, N equals 1/2. Whereas semi-annually is 2 times a year. So N is 2. We could say daily, and that would give us 365. There are lots of options. Okay, so we deal with compound interest. And whenever it's compounded nthly, daily, monthly, yearly, biannually, semi-annually, hourly, quarterly, any of these options, we're going to choose this formula. A of t equals P times 1 plus R over N to the NT. So we have here E. E is Euler's number. There are 2 buttons on your calculator that have the E option. Above the division symbol over on the right side of your calculator, you see an E on that button. And there's also an E above the LN on the left side of your calculator. There's an E to an X, and that's going to give you the option to plug a number into the exponent. Okay, so E is this irrational number. E is Euler's number. It goes on forever. And you can see here, this is a snippet of E to 1,000,000 digits here in the background. The numbers keep going, just like pi. E is associated with continuous growth. So for every other time we talk about, nthly, daily, monthly, quarterly, we're going to use that above formula. But when we start talking about continuous growth, for continuous, we have a different formula here. And the reason I bring this up right now, even though we're not going to really use E a lot or our E formula until we get towards the end of this unit, is because the number E is developed from my compound interest formula. So if I take my compound interest formula and I put in $1, a principal of 1, at a rate of 100%, so 100 divided by 100 gives us 1. For a total of 1 year, it would simplify down and look like this, right? So the only thing we have in this piece, 1 plus 1 over n to the n, is my n value. And so n is the number of times compounded. So if we look at compounding periods, and we look at making those compounding periods more frequent throughout the years. So if we compounded it annually, just once that year, we started with $1, we earned 100% interest. At the end of that 1 year, we would have $2. Semi-annually, 2 times a year, gives us just a little bit more. Quarterly, we're at $2.44. Daily, we're at $2.71. And if we look at hourly, we get this number here, 2.7181. 2.718. You see those numbers there? So what happens is, as we consider increasing the number of times we compound something, this output approaches an approximation of E. So this is how E is developed. And I just like to put it in here because I think it's interesting. All right, but E, whenever you have to do an E calculation in your homework, you're always going to use that E button on your calculator. E is approximately 2.718 is normally what I'm using if I have to write it on my paper as a decimal, but generally we're just going to leave it like E, the same as we did with pi, which is 3.14. So let's do a problem with interest compounded nthly. So suppose we have $2,500, that's what we start with, invested at 2.7% interest, compounded semi-annually. So what I'm getting from this is that I know my P is 2,500, my interest R is 0.027, and the number of times compounded semi-annually will be 2. So let's determine, for part A, a function that models the amount to which the investment grows after t years. So we need to set this up as a function. So we have A of t equals P times 1 plus R over N to the nt. All right, so I know what my R value is, and I also know what my N values are. All right, so I'm going to plug these numbers in. P is 2,500. My interest rate, R, is 0.027. And N, my number of times compounded, is 2. So I'm going to replace that there and then in my exponent. So this is my function which models the situation we are discussing here. When you are writing a function, you will always have an input variable, t, and an output variable, a of t. So we have to have an x and a y, or else it's not a function. And we can simplify this a little bit. I can go to my calculator and type 1 plus 0.027 divided by 2 into my calculator, and I get a decimal value that terminates. So I'm not getting a decimal that runs off of the screen. So in this situation, if I wanted to, I could take that and say, well, a of t is 2,500. That decimal in the parentheses is 1.0135, and we've raised it to the 2t power. So this is perfectly acceptable as well. But if when I was doing this calculation, if I got some decimal in there that ran off the screen, I would be hesitant to use that to create further calculations within the problem, because anytime I round a value or I put a rounded number on my paper, I create inaccuracy. And in math, we want to be as accurate as possible. So either one of these are fine for my original function. One other caveat I want to warn you about. Some of you are going to want to go ahead and multiply these numbers, right? Go ahead and give me a product there. However, we don't want to do that, and make sure you think about your order of operations, PEMDAS. So multiplying cannot occur until we deal with the exponent. And here I can't raise this to the 2t power yet because I don't know what 2t is. So we can't complete that multiplication yet. All right, so find the amount of money in the account after 18 years. That is t equals 18. And at this point, we're just going to take that t equals 18 and plug it into our function. So a of 18 equals 2,500 times 1.0135 to the 2 times 18. 2 times 18 is all in the exponent. And here's another place I see students run into issues is they can't get that typed in the calculator correctly. So I'm going to encourage you to go ahead, if you can do that calculation first. 2 times 18 is 36. Sometimes, especially if you have an older calculator and you are raising that 1.0135 to a power with the caret, if you type 2 times 18, that's only going to raise it to the second power, and then it's going to multiply by 18. So I just don't want you to make a mistake. I can't show you my calculator here. So you need to make sure that 2 times 18 is all in the exponent. All right, so if we plug this into our calculator, we find that a of 18 is equal to, we get a of 18 equals 4,051.306658, so 3,1. After 18 years, the amount of money in the account is $4,051.31. Okay, so the next part, after how many years will the account hold $5,000? So in this situation, $5,000 is my end amount, right? After how many years will the account hold $5,000? So that means we're taking our equation up here, and I'm putting 5,000 in as my end amount. And when I do that, I've got 5,000 equals 2,500, 1.0135 to the 2t. So after how many years, that means I'm looking for my t value. And in this situation, t is in the exponent. And we can't solve this equation yet. All right? So what we have to do, until we learn more about dealing with logarithms, which come in our next few videos, we're going to have to use our graphing calculator to help us. So what we'll do is we'll plug this in, and we're going to see an exponential curve that's going up. We're measuring t on the x-axis and the end amount, the money in the account, on the y-axis. And so when I go to set my window up, I'm going to set my x from 0 to maybe 30, and my y values are going to go from 0 to maybe 70 or 7,000. All right, so this is what I have in my y1, my function from up above. And what we need to do next is take that 5,000 and plug that into my y2. So the solution in this situation is going to be the point where they're intersecting. And on your TI calculator, if you choose the option second and then trace, which is actually going to help us calculate, as it says calculate above it, you're going to go down and choose option 5, which says intersect. And the calculator is going to say, well, choose near on the first curve, choose near this point of intersection on the second curve, and then guess. And so you're going to move your left and right cursor arrows near the point of intersection, and you're going to hit enter after each guess. So I'm going to go my first curve, on my second curve, and then guess. I hit enter 3 times. And when I do this, my calculator returns to me that that point is 25.84517, 5,000. So in this situation, when will we have $5,000 in the account? Roughly 25.8 years later. Okay, so we're just interpreting that point there.